Okay, let's make something very, very simple. Let me open the code. Look at this code. I'm going to stop turtlebot. Let me stop everything. Maybe just putting the score. بالعربي أين فتحنا؟ Look now, let me start row score. And then make rows topic list. Okay, this is what I have. I don't have even TF. Look at this simple code. This is now how we can actually program a transformation into ROS. We create a node, whatever it is. We just slip a little bit, and then we're going to broadcast the transform. Yourself can do the transform. Okay, if you want to do it. But the لما سوينا جزء scanner, في بداية الوقت of the scanner, I told you we need to publish transform for the laser scanner. You know the position is the map tree. Maybe you don't remember, but this is now how we can broadcast the transform. So we create an object from the package tf.transform broadcaster. I'm going to call it transform broadcaster. And then I need to define my transform. Okay, so we use send transform to publish this transform. But what is a transform? It has two things, rotation and translation. So I will define my rotation in quaternion, tf.transformation.quaternion from Euler. So here I'm going to use 0 for roll, pitch, and 90 degrees for the roll. Just a choice, you know. Okay? And then translation vector, I'm going just to put some random values. Yep. X, Y, and Z translations. This is my vector, X, Y, Z. And the current time, every transform it must have a time. And we are going to publish it. Okay? And then we will send this transform loop, transform underscore vector, this one. Then rotation in quaternion. Then the current time. One moment, just let me finish the explanation. I will put everything into one line. Okay, and finally, the current time, and finally, what is the parent frame and the child frame? Or I think child and parent. Child and parent. Now, this we make quaternion from Euler. The opposite. So this is roll, pitch, and Euler. The other one is Euler from quaternion. In this case, you provide the 4 values of the quaternion. And the two conversions. Here we convert something we know to something that we don't know. Okay? Quaternion is thing that is used by us. Sun transform, translation, rotation, current time, and which frames. Now I can do this translation, this transform, and check it. Okay, look now. I will run this code. Let's go here. and we make ROS run, ROS course, var2, broadcast, transform.py. Now we can do ROS topic list again. We have TF. Okay, I can make ROS run. What was the command for TF view? TF view frames. We can do the same thing. Look now. This is frame.pdf. Okay, Word is the parent, and robot frame. Okay, and this is the average rate. We did not specify. We can make sleep here if you want to reduce the rate. Yes. Okay, look now. I can do also ROS topic info or echo TF. Do you know these numbers? 1.2, 1.3, 0. Yeah. And what is this? This is 90 degrees, quaternion for 90 degrees. Okay? Yes. And now we have frame ID is the word, and the child frame ID is the robot frame. Okay. And now, if you add another frame, it's going to be here, because this is an array of all the frames. Yes. And the robot, every robot at the end is a series of frames. That's it. Okay. Look, it's very simple. Now we can do another sleep. For example, sleep.0.5 or time.sleep here. And you know, for example, for some frames, for example, Odom between Beijing and Odom, you have to publish frequently because, for example, in Islam or for advanced applications, you need to have information really instantaneously. You should not spend too much. But now I'm going just to try this. Yes, to do some time sleep and publish again. Let's check if okay, 2 hertz, 2 times a second, 0.5. Okay, so you can see how you can specify the average rate. I just added. So using this broadcaster, you know, you can do any broadcast between any frame. All you need to do, change your rotation quaternion, translation vector, and current time is the current time, and then the name of the frames. That's the skeleton for publishing any frame. This is present. Now this code I just did it today, but you can find here TF tutorials in ROS. It's not bad, you know, but I mean, explanation sometimes is a little bit tricky. I remember. Yeah.
Sometimes they focus on C.
No, it's same thing in C and in Python.
Okay.
But sometimes it's difficult. I'm going to explain here because this is one of the most critical topics in ROS. You know, it's not really easy to understand. If you read the documentation, you will find several scattered information. You cannot get it like fully in a row. Yeah. So now the second step, okay, but how is this useful for me? Now I know how to broadcast a frame. Yeah, but how this is useful? Let me show you an example. I'm going to run for now. Look at this application. We're going to have two turtle sim. ROS course start demo. This is the first time you see two turtles in turtle sim. So we're going to make a follower. When you move, the other one is going just to follow. Okay, I'm going to teleoperate now. Look. Try to catch it. Okay. So this is a wife that wants to have some money from her. Okay. Okay, so now we're going to see how we can actually do this using transformations. We can do this using like the same strategy that we did before, is to find the position of the first turtle, the position of the second turtle, calculate the distance and the orientation. Yeah, and using arctangent and all these different mathematical things. You know, with transformation is going to be straightforward. Okay, because now what's the idea? I'm going to attach a frame to turtle 1 and the frame to turtle 2, and then every time I will listen the transformation between both, and the transformation is going to give me the rotation and the translation. Based on this, I'm going to adjust the speed of turtle 2. Okay, you remember the exercise that we did, go to goal. Same thing. Now the goal here is moving. What we did here, the goal was fixed. Position and then it moves. Now the goal is moving, okay, updated. So I will know the update between the transformation, between the two frames. This is the idea. So let's look at the internals. We have here two files. We will start by TF broadcaster and then TF listener. Look at the broadcaster here. We're going to start a turtle bot, a turtle seam. And here, I'm going to broadcast a frame. So what we will do, we will create a subscriber to the topic turtle 1 pose or turtle 2 pose. Okay, so I'm going to take the name of the turtle from the parameter. It's possible to define parameters and get them into the code. I'm going to show you that. Okay, so for example, in the launch file, I can anticipate on this. Okay, so I can specify as parameter param name turtle and value turtle 1. So this value turtle name is going to be replaced by turtle 1. And for the second turtle is going to be replaced by turtle 2. Okay? I can do this manually if I want. But you know, this is just an elegant way. I can just write here, one for turtle 1 pose, one for turtle 2 pose. I have to make two broadcasters. But you can do one broadcaster that is customized based on the parameter. واضح? Yes, I'm going to explain the last file later. Okay, but now, if you don't want to use this one, what you have to do? You have to make a broadcaster for turtle 1 and the broadcaster for turtle 2. In this case, you don't have to bother with getting the parameter. But if you are going to use the launch file, and even I can add a parameter inside the command line. You remember when you do image view, we did image equal, and you give the name. So this is a parameter. Okay, you can define a parameter in the command line of ROS run, or you can define it also in the launch file. Voila. So at the end, we're going to just to take the turtle name here, put it here, whether it is turtle 1, turtle 2, and then subscribe to the pose. Okay, this is the pose callback. Let me call it pose callback. It makes more sense to me. And this subscriber is related to a certain name of the node here. Okay, pose callback, turtle name. This is a parameter. Yes. Because I will need the turtle name here to specify the frame. Look now, what I will do, I'm going to publish the frame attached to the turtle, okay, where the translation vector is going to be XY coordinate, and the rotation will be the orientation of the robot. And I'm going to create a frame that publishes between the turtle bot, the turtle node, and the word frame. واضحة ولا مش واضحة؟ شوف الآن. إذا الآن عنده X, Y coordinate. I'm going to create a frame here. So this is word. And this is now 0, 0 in the word. So the frame attached to the turtle, what will be the origin of this one? So the translation is X coordinate of the turtle and Y coordinate of the turtle. صح ولا لا? And the rotation will be the angle of the turtle, theta. صح ولا لا? Okay, so I'm going to attach a frame to this turtle. Look now. Huh? Using a broadcaster. Yes. It creates a frame. So look, now this frame is going to change its rotation vector and its translation vector every time the robot moves. واضح ولا؟ نفهموها step by step. So the transformation between word and turtle name frame will be the location of the robot and its orientation. عملنا العكس اللي شفت في الأودوم قبل اللي سويناه في الأودوم مع turtle bot frame. شفنا the transformation between odom and base link is the same as the odom pose of the robot. This is how it was done. Huh? No, we can do it without. Like you will see, transformation is going to make it easier to find the rotation and the orientation. Instead of making a callback function for the pose and then finding the orientation, finding all the different things, you will see later on in the subscriber how we can do it easily. Okay, for now, what we have done with this? We have created a frame attached to the robot. Okay, and what is the transformation between the robot and the word frame? XY as a translation and theta as rotation. Of course, here we have to convert theta to quaternion. Okay, شوف الكود هذا هو نفسه. You have understood this one. Same. What changed is here I'm going to have turtle frame, and here I have what? Here I have static translation vector and static rotation vector, which can, for example, if I define the transformation between the base link and the camera, I can have something static. But now I'm going to define the position of the robot with respect to the word frame. So it's going to be dynamic. As this one moves, okay, the position is going to move and the transformation is going to move. Yes. لا بعدين هكذا. It's after that. Yeah, but no? Where did you see it? Yeah, initially, yes. Yeah, it's 5, yes. Yes. So you can see now the translation vector is going to be XY coordinates, and the rotation is going to be the quaternion of the rotation angle here. No, we will see later on. We are not at this stage. Now we are just running. Look, let me run this code. Okay, I'm going to make a launch file here. New file. I'm going to call it launch. Okay, TF turtle theme broadcast. dot launch. I'm going to remove the other part. Okay, so I'm going to take the whole thing here. Okay, and I'm going to remove everything related to Turtle 2. And I don't want a listener. So now I just created what? I'm going to create Turtle Sim node, teleop, and another node that is the broadcaster that we have done now. Okay, where the value of the parameter will be Turtle 1. Let's see what happens. Okay, let's see what happens. So this is, I'm going to close it. TF. I have only one turtle. Okay, look now. Let's see the transformations. ROS topic list. We have TF. Okay, ROS topic echo TF. Word Turtle 1 frame 5.5 5.5. What is 5.5? It's the pose. Okay, if I make ROS topic echo Turtle 1 pose, same one. Because now my frame, I attached my frame to have the same position of the robot. It's going to move with it, with respect to the word frame. Okay? Just try to. Yes. And we will do the same for TurtleBot 2. Why? Because TurtleBot 2, Turtle Sim 2 needs to know its location as well. So we will know, this is what we will do. So we have a first turtle here and the second one here. So what we will do, this is the whole space. Okay, color field, no field. Okay, we're going to attach a frame here. Okay, using the broadcaster. Okay, and also I'm going to attach another frame here. So this frame will be located to the XY coordinates. Okay, so this is the X coordinate and this is here the Y coordinate. Voila. If this one moves, this frame moves again. It's attached. So same thing here. So now this is the word frame. Let me make it with another color. I want just to change the color. This is the word frame. Okay, of course I will measure the transformation between the word frame and Turtle 1 frame and the transformation between the word frame and Turtle 2 frame. Okay, and then ROS is going to give me automatically the transformation between Turtle 2 and Turtle 1, which is the relative distance and the relative orientation. كونت ROS. هذه الأشياء this is why ROS is very powerful. Okay, so for us, we're going to define the relation between this frame and this frame. Sorry, I come to you, Abeda. This is Turtle Sim 2 frame, and this is turtle sim1 frame, and this is word frame. So we will define transformation between word to tsim1 frame. And then we will define the transformation between word to turtle sim2 frame. And finally, ROS will give us the transformation between turtle sim1 or 2 frame to this one. And this one, what is this one? Is actually, yes, the distance here, translation, okay, distance. I can calculate by the translation, صح ولا لا? Plus rotation between the two robots. صح ولا لا؟ So it's like this. Okay. الداتا هذه you publish it. It's now the broadcaster is going to publish this. Okay. I can do something wrong, you know. Publish it. It's up to you. You know. You define the logic. So what is our logic here? Look. The frame attached is going to have, okay, sun translation vector, quaternion vector, which is this one, the xy coordinates, translation, and the theta is the rotation. واضحة الآن. Okay. So now this code that is running is just this frame. Now I want to do also the second frame. Look now. If I do ROS echo, I have only one frame, word to turtle one, only. Let me add another one now. So you can define another file, as I mentioned to you, Lear broadcaster 2 for turtlebot 1. But now we have the launch file, it makes things much easier. So what I will do, I will define another node in the launch file. Same thing. The only thing that changes, the param name. Okay, when I change the param name, I'm going to have a different frame name. واضح ولا لا؟ Yes, turtle2 underscore frame. Okay, and now let me close this code running. And now it's going to open. Okay. I missed something to change in the launch file. This is turtle2, the node. I changed the param name. Yeah, we changed the value only. Param name is turtle. This is the param name. Turtle. It must be the same. Yeah, but the node name must be different. That's why. Okay, now we don't see here the second turtle, but we have the second TF because now we have to spawn the turtle. You know what is the spawning service we have to call it. We are going to call it in the listener later on. But now if I do ROS topic echo TF, we should have both, or we still have one. We have only one. Maybe because the node is still not created. Yeah, just like turtle tf broadcaster.py. In principle, okay. Let me close everything. I'm not sure whether we're going to see it now. I didn't try that. No score. Then ROS launch, ROS scores, R2, TF. Turtle scene broadcast. Turtle 2 TF broadcaster. Yeah, we do have. Let me now try. Yeah, we have the ROS topic, echo TF. It's not broadcasted for some reason. Did I miss anything? Yeah, we have to spawn. Yeah, I understand why. Because we don't have Turtle 2. Look, here we subscribe to Turtle 2 post, and there is no publisher to it. If I need to create a second Turtle 2, that's why. Okay. Now the subscriber did not start, so the transform is not even broadcasted. That is why. Okay. Now we understand the logic. Okay. So now the next step. Of course, now we can create the frame. It's possible, but of course we need to create also the second turtle scene, and we will attach a listener. So now, how we're going to make the following? We would like to calculate what is the distance and orientation. Maybe this robot is rotated like this. Okay. Okay. So it's looking at this direction, and this robot can be, for example, looking at this direction. Okay. So I'm going to calculate the distance between this frame and this frame. That is the translation. And I will calculate also the rotation. But here I'm going just to control the translation to make it simple. Okay. So this is how it looks like. I'm going to do a listener. This is the listener code. Okay. So first of all, we have to make a transform listener. This is something new. So what we'll do, the transform listener is going to listen, like we do ROS topic echo. TF. We listen the transformations. Okay. But of course, we need to create our second turtle. We're going to use the service. We have already used the command line before. And I think in one of the exercises, there is this command that is spawn and reset and so on. So it's going just to create a turtle at the position 4, orientation 0, y equal to 2, and the name is equal to turtle 2. This is the name. Then what we will do, we will control. Now this is a control problem. Like go to goal, we're going to calculate the velocity of the follower. So the velocity of the follower, مثل ما سوينا في go to goal, is proportional to the distance. So if I find the distance, at the end, you will find linear velocity will be something multiplied by the distance, and the angular velocity is the arc tangent like we did before. But now what's the difference? Is how to find the orientation and how to find the translation. That's the difference. Before what we did the subscribe callback, post callback, and then we find the XY coordinates, and then we calculate these values. Sahwala. Okay, I can show you the original code. In SRC, here, just to remember, in motion, turtle scene move. So what we did, فيها go to goal هذه ولا؟ Where is go to goal? Yeah, here what we did subscriber to the post. Here it's without a distance. No, we didn't even do a subscriber to the pose here. It was in the cleaner, turtle scene cleaner, yes. Subscriber to the pose, and then the distance moved is equal to this formula. And even for the go to goal, this is what are interested to. In this case, we have used go to goal as a fixed point. And we calculate the linear velocity. And I told you that here we use a constant for PID controller. And here we know the XY coordinates. of the goal location. Now what is the goal location? It's turtle 1. And the one that is going to move is turtle 2. Okay, so I need to find the same thing. Okay, I need to find the position of turtle 1 with respect to the turtle 2. This is what I want to do. And this is how we can do it in the listener. We're going to listen, okay, transform listener. We're going to listen turtle 2 frame, the transform between turtle 2 frame and turtle 1 frame. So turtle 2 is the child frame and turtle 1 is the parent frame. Yeah, this is going to give us the position of turtle 1 with respect to the turtle 2. Yes, transformation. So the transformation is going to return to us translation plus rotation. اللي هي الاكس of turtle 1 with respect to turtle 2 and the rotation of turtle 1 with respect to turtle 2. هذه اللي قبلنا احنا نسوي فيها بالارك tangent and everything. So the x follower in turtle 1 frame is equal to translation 0 and the y follower in turtle 1 frame is equal to translation 1. Yes, it's an array. It contains the value of x, y, z. What is the translation? It's a vector. X, Y, Z coordinates. And the other one is the quaternion. The rotation is the quaternion. Okay, what is the angular here? Okay, and here we calculate the arc tangent between the two frames. That's all. And then it's going to move until it reaches the goal. So basically, it is the same behavior as here, exactly the same. What is the difference? Here we have used post callback in order to find the desired angle between the goal location and the current location. Okay, and here we have used the transformation in order to find the relative position between both frames. So now doing that, we can go to the launch file. I just add the listener here, and the listener is going to spawn a turtle and then make it move as the whole story. Look now, if I use that again, start. Okay. So this turtle is listening to the frame of the other one, calculating the translation using the XY coordinates. And using the XY coordinate, it can know what is the orientation it has to turn. Okay. And then, look, every time you move, let me show you here. The yoke is already there, but I can open another terminal and we do ROS topic echo. Look now. ROS topic echo TF. And look, we can make ROS TF is going to give us the transformation between any two frames. I can now say between turtle 2 underscore frame and the other frame is turtle 1 underscore frame. It's going to give me only this one. Is it turtle 1 frame, turtle 2 frame? No, but I want between two frames. Maybe I forgot about that. ROS topic. Echo TF frame 1. I know there is a way. TF echo. Yes, TF.TF echo. ROS run TF echo. Look now, I can find between turtle2 frame and turtle1. What is the transformation now? Look, I'm going now to tell you up. Look at the transformation. Translation vector is changing. Look, changing, and then it becomes 0. Okay, we did not define explicitly transformation between turtle2 frame and turtle1 frame. But in ROS, since we have defined the transformation between turtle1 and world, turtle2 and world, we are able to define between turtle2 and turtle1. We are able to define between turtle1 and turtle2. Okay, so ROS is going to make all the computations needed for you in order to find the transformations. Ish? Value of 5. Now it's not changing because the two robots are moving. Look, I'm going to move the robot again. The value of y is changing. Okay, look, both the translation and the rotation. Okay, the concept of TF is not easy in the beginning. Okay, لكن, you know, it's the same thing that I have presented in the previous theoretical lecture. Now this is the implementation in ROS. Okay, all you need to do to think is that there are frames and there are transformations between frames, and these are the tools to know these transformations. This is very simple. Now, probably the most critical is how to use this, for example, to make the robot move. You know, this will come with practice. That's normal. If you get the overall idea and you miss some of the details, it's not a problem. It's very normal. I personally spend a lot of time in order to understand this effectively. Okay, but with time and with more practice, you're going to know this more and more. And usually we're not going to use this into all these details, but now you understand what is being done in the background. When we talk later on about navigation, when we talk about map and you say map frame and position in the map, you know that every position that you get in a topic is based on this being done in the background. But most of the time you're going to use the topics in order to get the positions. In some cases, you can use this frame. So for example here, I can finish by a code, and maybe I will give you the code to look more carefully at home. So here, I have a complete tutorial on GetTech.edu that I actually did. TurtleBot tutorials and TurtleBot free motion in space. So this is going to a generalization of what we have done before. هنقبل دايما نسوي motion, we use the time multiplied in order to calculate the distance. Time multiplied by the speed or the Euclidean distance and so on using the course. So here you can read this tutorial. It's very well detailed. I did it myself and I have written it in all the details. So it's going to be a summary. And here I present 3 different versions of the motion. 2 of them using TF transformations, and 1 of them uses the Euclidean distance that we did before using the post callback. Okay, look now here, for example. I think you remember the code. I did it in C++ and in Python as well. So this is the part that this is in C++. Let me show you the whole code. It's better. Python code. I have the whole code here. I'm going to give you some information about how we can do it. But don't worry, if you find it complicated, don't worry, you know, it's complicated. You know, it's something that it's something that you understand better. This is, for example, the first version of Move. Okay, I think this is, you know what is this one? We create a twist message. Initially, everything is 0. We publish a 0 velocity, the speed. Now, we're going to do a listener, transformation listener. And then, first of all, usually we are not sure that the transform exists. So before trying to make lookup transform, we can check whether the transform is being published or not. And for this, we can use wait for transform. We're going to wait here for 10 seconds. If in 10 seconds we find the transform, we're going to proceed. Otherwise, we'll make an exception. Okay? And then if the transform exists, I'm going to calculate the transform between what? So what does this give to me? What is this going to give to me? So this transform is between what and what? Odom and phase, yeah. So what this translation is going to represent? The position with respect to Odom. Sahul. Trans. And the rotation will represent the rotation and the orientation. That's it. Okay. So now I have the rotation. I can calculate the distance, the translation, because this is with respect to Odom. So this is the distance. Yes, move. Yeah, so this is start. Start is actually what? And then we have distance moved is equal to 0. We don't need start here, actually. Okay, we're going to calculate the distance moved. And every time we're going to listen the transformation between Odom and base footprint, which is going to give us the new coordinates, the new x and y. Okay, based on the new x and y, we can calculate the distance between start and end. This is the distance moved. If you look for a frame that does not exist, so transform does not exist. مثلا, you don't have something called Odom. مثلا, you don't have. مثلا, do we have a frame called map? Imagine that I make lookup transform, base footprint, and map. So what it will do? Nothing. Okay. I'm going to explain more of this. Maybe now we are at the end of the lecture. I'm going to come back on this in the future. But now what I want you to understand, we have frames, and we can, in ROS, we can find the transformation between any two frames. Okay, and you have the code. You know, just copy paste the code but use it to copy paste in the best way. Now, I think what we should work a little bit more is how to think about the behavior-based development approach. Because sometimes you have an algorithm, but you don't know how to translate it into behaviors. Okay? So like you do state 1, state 2, state 3, how to make the links between them. This is what is missing. But we are going to work a little bit more on this, because the development for programs for robots are different from like what you do in Java or software development. I noticed this from the exams, but it's not a big deal. We're going to have some exercises on how to think about behavior-based development for the robots. Okay, so that's all for today. I'm going to send you an assignment, but not this one. I would like that you learn more about computer vision. So there are some tutorials which I find interesting on object detection, on face detection, face recognition using deep learning. Okay, so I'm going to assign a tutorial for every 2 students to work on it, understand it, and then extend it so that the robot becomes more smart and intelligent. And then you will present us the approach, okay, of the computer vision. For example, if it is about face detection, you explain us how face detection is made and how it can run on the robot. For example, you can detect a face and just follow this face, or you can detect an object and okay, you say something like find this object, or we can do something like this. Okay, for example, we can ask the robot to find the bottle. That's easy. Now, all the problem is how to recognize the bottle. There are now easy tools in OpenCV that you can use based on deep learning with pre-trained deep learning networks. You can run them on the robot. When you find something, it's going to give you a bounding box. You know the center of the bounding box, and then you can orientate the robot toward it as a goal location. Okay? So I want to build more and more smart applications using robots. So I will give you a series of tutorials. Every 2 students will work on this and then develop an application to demonstrate how you can do it for the robot. Okay. Any question? Okay, that's all.
So for this, you need to refer back. Is this the video?
I'm going to give you these videos. I will put them on YouTube. But don't worry, I'm going to come back again and again because this topic is a little bit.
Yeah, it's very abstract. The more you practice.
So about the camera, can we know the selection?
Mm-hmm.
Like you said,
Yeah.
can we know the selection? Yeah?
Which destination?
This is how I'm thinking about it.
Stop.